This is the third video for Mr. Sweeney's AP Physics C class on the one-dimensional motion packet. For this video, you're going to want to have your reference tables out, your AP Physics C reference tables, and have them opened up to the second page where we have some equations. We're going to talk about some constant acceleration equations as well as acceleration due to gravity or free fall. So starting constant acceleration, our goal here is to start developing some equations, and we'll see these equations in our reference tables. And the first idea that we're going to use to develop these equations is that if our acceleration is constant, that means the instantaneous acceleration, or the acceleration anywhere along that path, will be equal to the average acceleration that we'd find over that path. And looking at that, we can see that acceleration equals average acceleration, and this is only for constant acceleration, which average acceleration being equal to velocity minus velocity initial divided by time minus 0. Now we minus 0 from time, or we subtract 0 from time, because when over our time period we'll set our initial time equal to 0. Simplifying this equation further and dropping out the average acceleration, we find that acceleration is equal to velocity minus velocity initial divided by time. And solving this equation for velocity gives us the first equation that we have in our reference tables under mechanics, and that is velocity equals velocity initial plus acceleration times time. Notice that in your reference tables, all these have a subscript of x, referring to the fact that they're all moving in one dimension. I leave the x's off here for clarity, but realize that this velocity all needs to be moving in the same direction, and that's what they're giving by for the x. So our first equation allowed us to solve for velocity and give the relationship between velocity, velocity initial, acceleration, and time. If we want to solve for the displacement, or the change in position of an object, we have to first look at our initial or our average velocity as the sum of initial velocity and velocity divided by 2. So if you take these two velocities, our initial condition, our final condition, and divide that by 2, we would find that this velocity gives us an average velocity. Now prior we had solved for velocity being equal to velocity initial plus acceleration times time. So we want to substitute in for our velocity in the equation above this velocity initial plus acceleration times time. And you can see that down below. I've highlighted it in red so you can see where the substitution took place. We've just replaced the velocity in the equation up above with velocity initial plus acceleration times time. Simplifying this equation allows us to get to velocity initial plus 1/2 acceleration times time from our prior. But this doesn't quite give us our position equation that we were looking for, where we want to find our change in position. To find our change in position, we have to take this average velocity and multiply it by time, because velocity average equals change in position divided by time. So if we multiply the left-hand side by time, we will get change in position. And since we multiply the left-hand side by time, we have to multiply the right-hand side by time as well. And that gives us our change in position equals velocity initial times time plus 1/2 acceleration times time squared. And you'll see this as the second equation in your AP Physics C reference tables, the second one from the top. Now we don't always have time included in our equations, so instead of having an equation that relies on time, we can also, since now we have two equations that solve for time, substitute one of the equations into the other. And we're going to solve our first equation that we derived, velocity equals velocity initial plus acceleration times time, for t, and then we'll substitute that into our second equation that we derived, change in position equals velocity initial times t plus 1/2 at squared. By solving the first one for t and substituting it for the second one, we'll have an expression then that relates these variables, velocity, velocity initial, acceleration, and time, and change in position, or acceleration is not included, change in position and acceleration for these variables. So solving for t, it's t equals change in velocity, or velocity minus velocity initial, times divided by time. And we want to take this velocity minus velocity initial divided by time and substitute it into the equation above, and that yields us this expression. Change in position equals velocity initial multiplied by change in velocity divided by acceleration, and to that we add 1/2 acceleration times change in position, or change in velocity divided by acceleration squared. So this is just substituting in for t in the second equation what t equaled to in the first equation. Now we want to simplify this equation, and in that simplification we're going to simplify it, and it takes the form change in position equals velocity initial times velocity minus velocity initial squared divided by a plus 1/2 velocity squared minus velocity initial times velocity plus velocity initial squared divided by a. Now this equation does not allow us still to simplify yet, because we have a couple things here. First, we do not have a common denominator on our two terms in the right, and we want to get that to be just a. So we'll multiply both sides of this equation by 2 in order to eliminate that 1/2 that's over there. That'll allow us to combine these two equations. So that way we can write the right-hand side of the equation as one term all divided by a. And when we multiply by 2 and combine those two terms, we get 2 times our change in position equals 2 times velocity initial times velocity minus 2 velocity initial squared plus velocity squared minus 2 velocity initial times velocity plus velocity initial squared divided by a. That's enough out of you, Jared. Taking this expression, on the top of this term on the right hand side, we can see that we can cancel a lot of these out. The 2 velocity initial velocity cancels out with the negative 2 velocity initial velocity, and you can see that we have a negative 2 velocity initial squared. That cancels out with one of the velocity initial squares that's at the end, leaving us with a more simplified equation. 2 times change in position equals velocity squared minus velocity initial squared divided by acceleration. And having it this far simplified, we can then simplify and put it into a familiar form of velocity squared equals velocity initial squared plus 2 times acceleration multiplied by the change in position. This is the third equation that we have in our reference tables down from the top. Notice that all three of these equations are fundamentally derived from two ideas. The first one being that the average velocity is velocity initial plus velocity final divided by 2, as well as the fact that acceleration is equal to change in velocity divided by time. So those two expressions are all you need to solve the full gambit, and they've taken these equations and combined them in certain ways where we have a missing variable, but that missing variable changes from equation to equation. Now looking at this, when we're talking about constant acceleration, probably the most prominent example of constant acceleration in our environment is the example of free fall. When any airborne object near the Earth's surface is in free fall, meaning there's nothing under it and it is free to fall, it will fall with a constant acceleration of 9.81 meters per second squared towards the center of the Earth. Now this only occurs at or around the surface of the Earth. So if you are in the upper parts of the atmosphere or under the Earth's surface, you'll find that your acceleration due to gravity that's causing free fall varies with your height, but in general that variance is very, very small for the portion of the Earth's surface that we inhabit. So this free fall motion, it is due to the gravitational attraction of Earth, and we'll talk about that in a further unit. And this acceleration due to gravity is given a special symbol, and that symbol is the lowercase g. Now, if we're talking about free fall as a constant acceleration, we have to consider the fact that air resistance can alter what our acceleration due is to gravity. So typically, in most problems, we will neglect air resistance. Air resistance is a function of partly the shape of the object and what surface area is being exposed, as well as the drag coefficient. And we'll talk about that in a further unit. The main idea that you want to realize now is that air resistance will always cause this acceleration to decrease in magnitude. And this decrease in the magnitude of the acceleration caused by gravity depends on how fast the object is moving. So the faster the object is moving, the more air resistance will come into play here. In fact, at one point, the air resistance will be so much that it will actually cancel out all the acceleration due to gravity. And this is what we call terminal velocity, when all the drag forces are matching up with all the forces that are pulling it. But we're talking about accelerations now, and we'll talk about drag forces and dragging coefficients in our next unit. I'd like to solve a problem that has to do with acceleration due to gravity, and we're going to use the kinematic equations that we derived and that are found in your reference tables to do so. So in this problem, there is a ball thrown straight up in the air with a speed of 12 meters per second from a window that's located 10 meters above the ground. We want to know how long it takes this ball to reach its maximum height. Please note that I have a typo here, and what I'm looking at is 12 meters per second, not 12 meters per second squared. So to solve this problem, we're going to use the equation velocity equals velocity initial plus acceleration times time, because we have our velocity. We know at the maximum height, when it reaches its peak, our velocity is 0, and our initial velocity is 12 meters per second. Our acceleration is going to be 9.8 meters per second squared, and it's going to be negative because downwards is our negative direction. And we have a time that we really haven't found yet. So this is what we're trying to solve for, is this time. Substituting in our values, you can see that you have 0 meters per second equals 12 meters per second plus 9.81 meters per second squared times time. And that gives us a value of 1.22 seconds. So that's how long it takes us to reach the peak when we throw this from that 10 meter tall height. So if we want to find out what the maximum height the ball achieves is, we're going to use the equation position equals initial position plus velocity initial times time plus 1/2 at squared. Substituting into this for the values given, we have position equals 10 meters plus 12 meters per second times 1.22 seconds plus 1/2 multiplied by negative 9.81 meters per second squared times 1.22 seconds squared. Notice that our negative 9.81 meters per second squared means that as this object rises in the air, its position will, or the rate at which its position changes, will decrease as we go. This is the term that brings it to 0 at our peak. Solving this for x, we get a position of 17.3 meters above the ground. This is not above the 10 meter window that we threw it from. This is above the ground below. So we're 17.3 meters above the ground, would mean that we're 7.3 meters above our initial position that we threw it from at the window. And lastly, they want to know what velocity does this ball achieve when it reaches the ground. Again, I have another typo in my notes. It says we'll use the equation velocity squared equals velocity initial squared plus 2a times change in position. Substituting in for this, we find that velocity squared equals 12 meters per second squared plus 2 times 9.81 meters per second. And our change in position, initially we were at 0, and we ended up, or we're at 0 at the ground, and we started at 10 meters above. So our change in position is negative 10 meters. And solving this out, we find that we end up with a velocity at the end of 18.4 meters per second. And this is downwards. So you could say negative 18.4 meters per second. You could also say that the velocity is 18.4 meters per second downward. They both mean the same thing. This is it for your acceleration due to gravity examples. If you have any questions, you can come see me after class, and have a good one.